Picture this. You're an astronomer working the night shift at the Pan-STARRS telescope in Hawaii. It's October 19th, 2017, and you're doing what astronomers have done for centuries, scanning the heavens, cataloging the predictable dance of celestial bodies. Then you spot something that makes you do a double take. There's a red dot moving across your screen, but it's moving asterisk, wrong asterisk. Too fast, too direct. This isn't following any orbit you recognize. What Robert Warwick discovered that night would challenge everything we thought we knew about our cosmic neighborhood. He'd found something that had traveled from beyond the stars, the first confirmed visitor from another solar system. But here's where our story gets interesting. The more scientists studied this object, the more it defied explanation. They named it Oumuamua, Hawaiian for scout or messenger from afar. Little did they know how prophetic that name would become. Within hours of Warwick's discovery, telescopes around the world swung toward this mysterious visitor. The initial excitement was palpable. Finally, humanity had detected an interstellar object passing through our solar system. The confirmation process moved at lightning speed. The data was unmistakable. This thing had come from the direction of the constellation Lyra, traveling at over 87,000 kilometers per hour relative to the sun. But as the observations poured in, excitement began mixing with bewilderment. This wasn't behaving like any asteroid or comet anyone had ever studied. First, there was its shape. Initial analysis suggested something unprecedented, an object roughly 10 times longer than it was wide. Imagine a cosmic cigar tumbling end over end through space. Natural objects simply aren't found in such extreme proportions. Asteroids are typically rounded by eons of collisions. Comets are usually irregular, but nothing approaches this level of elongation. The tumbling motion itself was peculiar. Oumuamua rotated every 7.3 hours, which might sound normal until you consider what should happen to objects during millions of years of interstellar travel. Space isn't empty, there's dust, gas, radiation. These forces should gradually slow rotation, not preserve this kind of active tumbling. Then there was its color. Oumuamua appeared distinctly reddish, similar to objects in the outer solar system that have been baked by cosmic radiation for eons. This suggested extreme age, perhaps hundreds of millions of years drifting between the star's dot. As word spread through the astronomical community, the initial celebration began giving way to head-scratching. The European Southern Observatory's very large telescope provided the most detailed observations possible. What they found only deepened the puzzle. Oumuamua showed no signs of the dust or gas emissions typical of comets. Its surface appeared remarkably uniform, almost metallic in its reflective properties. More troubling were the trajectory calculations. When scientists traced Oumuamua's path backward through space, they couldn't identify any nearby star system it might have originated from. It seemed to come from nowhere, or more precisely, from the general direction of the Vega system, but Vega was in the wrong position when the object would have passed through that region dot by November 2017. As Oumuamua raced away from the inner solar system, astronomers realized they were dealing with something unprecedented. Every attempt to categorize this visitor ran up against its anomalous properties. It wasn't quite a comet, wasn't quite an asteroid, and didn't fit the models for how interstellar objects should behave. The scientific community found itself facing an uncomfortable reality. Their first confirmed interstellar visitor refused to conform to any known category of space object. Oumuamua was forcing them to confront the possibility that our understanding of what's possible in space might be incomplete. As the object disappeared into the outer darkness. Racing toward the constellation Pegasus, it left behind more questions than answers. How could something so elongated form naturally? Why didn't it show comet-like activity despite passing close to the sun? Where did it really come from? Most unsettling of all, what if everything we assumed about Oumuamua being a natural object was wrong? As observational data accumulated through late 2017, scientists began recognizing just how many fundamental expectations this visitor violated. Each new measurement seemed to deepen the mystery rather than resolve it. Let's start with that extraordinary shape. When astronomers talk about an object being elongated, they usually mean something maybe twice as long as it is wide. Oumuamua's 10-to-1 ratio places it in uncharted territory. To put this in perspective, imagine stretching a football until it's shaped like a baseball bat, then stretching it further until it resembles a javelin. Dr. Robert Wierig admitted the shape defied their models. The most elongated objects we've seen in our solar system are no more than 3 times longer than they are wide. Natural formation processes simply don't create such extreme proportions. What makes this even stranger is structural stability. An object this elongated should be incredibly fragile. Yet Oumuamua appeared solid and intact. The rotation data added another layer of oddity. That 7.3-hour tumbling period remained remarkably consistent throughout observations. But objects millions of years old should barely be spinning at all, not maintaining this vigorous tumbling motion. Even more puzzling was the complete absence of any visible coma or tail. When comets approach the sun, solar heating vaporizes surface materials, creating those beautiful streaming tails we're familiar with. Oumuamua passed within 37 million kilometers of the sun, close enough that any volatile materials should have begun outgassing, dramatically. Instead, scientists observed nothing. No dust clouds, no gas emissions, no tail formation whatsoever. Dr. Karen Meach from the University of Hawaii described their bewilderment. We expected to see the usual comet activity, but Oumuamua remained completely inert. It was like watching a stone pass through a furnace without even getting warm. Then came the acceleration anomaly, perhaps the most unsettling discovery of all. In July 2018, detailed analysis revealed something extraordinary. The object was speeding up in ways that couldn't be explained by gravitational forces alone. Marco Micheli, leading the European Space Agency team that made this discovery, described their shock. We expected Oumuamua to slow down due to gravitational attraction to the sun. Instead, we measured a small but definite acceleration away from the sun. This non-gravitational acceleration was tiny but utterly consistent and directed away from the sun. Natural explanations for such acceleration typically involve outgassing the rocket, effective material streaming off a comet's surface. But remember, Oumuamua showed absolutely no signs of such activity. The tumbling pattern presented its own problems. Computer models suggested that an object with Oumuamua's shape should have chaotic tumbling motion. Instead, observations showed surprisingly regular rotation around a single axis, physically improbable for such an elongated object. Finally, there were the optical properties that just didn't add up. Oumuamua's surface appeared unusually reflective for such an ancient object, yet showed that characteristic reddish color associated with extreme age. These properties seemed contradictory. Spectroscopic analysis revealed another oddity. The object's surface showed no clear mineral signatures. Most asteroids display distinct spectral features corresponding to specific rock types. Oumuamua's spectrum was remarkably featureless, almost as if its surface was designed to avoid revealing its composition. By early 2018, the astronomical community was grappling with an uncomfortable truth. Every standard model for natural space objects failed to account for Oumuamua's full suite of characteristics. The shape, rotation, composition, acceleration, and surface properties formed a combination that didn't match any known category of celestial body. Dr. Avi Loeb from Harvard University summarized the growing consensus. Oumuamua exhibited several anomalies relative to expectations for a natural object. The puzzle is how to explain all of these anomalies simultaneously with a single, coherent theory. As Oumuamua disappeared beyond the reach of Earth's telescopes, it left behind a scientific community forced to confront an unsettling possibility. Perhaps their assumption that this was a natural object needed to be questioned. A scientific method demands that researchers exhaust all conventional explanations before considering more exotic possibilities. As Oumuamua data was analyzed throughout 2018 and 2019, astronomers proposed increasingly creative theories. Each attempt revealed just how difficult it was to explain this object using known physics. The most ambitious natural explanation came from Daryl Seligman at the University of Chicago. His hydrogen iceberg theory proposed that Oumuamua was composed entirely of solid hydrogen. This exotic composition could potentially explain several anomalies simultaneously. The lightweight material could account for acceleration through sublimation without visible outgassing, but the physics proved problematic. Solid hydrogen only exists at temperatures near absolute zero. The sublimation rate needed to explain Oumuamua's acceleration would require losing about 10% of its mass during solar approach. Yet observations showed no evidence of this process. What if Oumuamua wasn't natural at all? **** Chapter 4 The Alien Probe Hypothesis ***** when Harvard's Professor Avi Loeb first suggested that Oumuamua might be artificial. The reaction ranged from skeptical to dismissive. But Loeb wasn't some fringe theorist. He was chair of Harvard's astronomy department with hundreds of peer-reviewed papers. His hypothesis deserved serious consideration. Loeb's light cell theory emerged from a simple question. What if we stopped assuming Oumuamua was natural and asked what artificial object would exhibit these exact characteristics? The answer was surprisingly specific: a solar sail designed for interstellar travel. Solar sails represent real technology that NASA actively develops. These ultra-thin reflective surfaces harness radiation pressure from starlight for propulsion. Japan's Icarus probe successfully demonstrated solar sailing in 2010. For interstellar distances, solar sailing offers unique advantages: continuous acceleration without fuel. Requirements. Loeb's analysis showed that a light sail roughly 100 meters in diameter and less than a millimeter thick would exhibit exactly Oumuamua's observed properties. The extreme thinness would create apparent elongation when viewed edge-on. The minimal thickness would make it incredibly lightweight, explaining the acceleration from solar radiation pressure. The light cell explanation is the simplest theory that explains all of Oumuamua's anomalies simultaneously, Loeb explained. Unlike exotic natural explanations, this requires no new physics, just technology we already understand. The tumbling motion made perfect sense for a derelict sail. Without active attitude control, such objects would naturally tumble through space. The stable rotation suggested rigid structure rather than flexible membrane, perhaps indicating ancient, non-functional technology. Even the missing outgassing fit the artificial hypothesis. Manufactured objects designed for space travel would logically use non-volatile materials. The featureless spectrum and unusual reflectivity could indicate artificial surface treatments optimized for specific functions. The trajectory analysis provided intriguing support. Unlike natural objects ejected randomly from birth systems, Oumuamua's path showed it had been traveling through the local standard of rest, moving with the average motion of nearby stars. This suggested either unlikely coincidence or deliberate trajectory planning. Historical precedent existed for considering artificial explanations. When pulsars were discovered in 1967, their regular radio pulses led astronomers to briefly consider alien beacons. The phenomena was dubbed LGM, Little Green Men, before natural explanations emerged. Science progresses by considering all possibilities. The artificial hypothesis also provided testable predictions. If Oumuamua represented alien technology, humanity might expect similar objects in the future. Advanced civilizations capable of interstellar travel would likely deploy multiple probes. Dr. Seth Shostak from SETI acknowledged the importance of considering all possibilities. The artificial hypothesis is testable and falsifiable, key requirements for legitimate scientific inquiry. Whether or not it's correct, investigating such possibilities advances our understanding. Loeb's analysis considered various forms of alien technology, Light sails represented just one possibility. The object could be debris from a larger structure or active technology employing unknown propulsion methods. The consistent acceleration might indicate controlled thrust rather than passive effects. Critics argued that extraordinary claims required extraordinary evidence, and Oumuamua's anomalies didn't definitively prove artificial origins. However, Loeb countered with statistical arguments. If advanced civilizations commonly deploy interstellar probes, such objects might be abundant in galactic space. The question isn't whether alien technology exists in space, Loeb argued, but whether we're finally capable of recognizing it when we see it. As scientific debate intensified, the artificial hypothesis gained grudging respect even from skeptics. Whether or not Oumuamua was actually alien technology, seriously considering that possibility forced astronomers to examine their assumptions and develop better criteria for identifying artificial objects. The mystery remained unsolved, but the questions had evolved. Instead of simply asking what natural process created Oumuamua, scientists began wondering, how would we recognize alien technology if it visited our solar system? If we accept the possibility that Oumuamua might be artificial, an entire spectrum of scenarios opens up. Let's explore what forms alien technology might take and how each aligns with the evidence the active probe scenario suggests. Oumuamua could represent a functional reconnaissance mission. This gains credibility when examining the object's trajectory rather than following a random path. It brought the object remarkably close to several major planets in our solar system. The timing was particularly intriguing. Oumuamua passed closest to the Sun in September 2017, then continued past Earth's orbit, approaching Mars before heading toward Jupiter's vicinity. An intelligence-gathering mission would logically target the most interesting regions. Exactly this path, Dr. Loeb noted this alignment. The trajectory suggests either remarkable coincidence or purposeful navigation toward regions where planetary activity would be most observable. An active probe might use gravity, assist while allowing detailed observations of multiple worlds, but perhaps more likely is the ancient derelict scenario. Interstellar travel requires enormous timescales, even at Oumuamua's speed. Journeying between nearby star systems takes hundreds of thousands of years. Any such technology might represent civilizations that existed long before Earth developed complex life. Oumuamua could be debris from a technological civilization that flourished billions of years ago. Ancient derelict technology would explain many puzzling characteristics: non-functional equipment tumbling through space, structural integrity persisting through durable materials, acceleration from passive effects like residual outgassing or radiation pressure on surfaces designed for different purposes. The Bracewell probe concept adds another dimension. Named after radio astronomer Ronald Bracewell, these theoretical devices represent self-replicating interstellar probes designed to explore and monitor galactic civilizations. Rather than attempting real-time communication across impossible distances, Advanced species might deploy autonomous probe networks. Oumuamua's behavior could fit Bracewell probe characteristics remarkably well. The trajectory through the local standard of rest suggests deliberate navigation rather than random ejection from another system. Such probes might travel between star systems, conducting surveillance before continuing to their next targets. The timing raises intriguing questions. Humanity has possessed radio technology for only a century, yet we detected this anomalous object just as our capabilities reached sufficient sophistication. Could this represent more than coincidence? A monitoring probe might activate when detecting technological signatures, with Oumuamua's acceleration indicating course corrections to optimize observations. Even more speculative is the deliberate camouflage hypothesis. Advanced civilizations conducting covert observations with logically designed probes to appear natural initially. Only detailed analysis would reveal artificial nature. Exactly what happened with Oumuamua, that such camouflage serves obvious purposes. Primitive civilizations might react unpredictably to obvious alien visitors. Disguising probes allows unobtrusive monitoring while avoiding potential interference with natural development. The camouflage theory explains Oumuamua's elusiveness, surface properties appearing natural combined with behavior just anomalous enough to puzzle. Scientists, finally, consider the monitoring network theory. Rather than representing a single probe, Oumuamua might be one component of vast surveillance infrastructure maintained by galactic civilizations. Such networks could monitor technological species development across thousands of star systems simultaneously. This scenario has profound implications. If monitoring networks exist, our development might already be cataloged by intelligences beyond current comprehension. Oumuamua's visit could represent routine data collection by networks, operating for millions of years. The statistical argument is compelling. If advanced civilizations commonly deploy interstellar monitoring systems, the galaxy might contain millions of such objects. Our detection could simply represent the first time human technology became sophisticated enough to recognize artificial signatures among natural cosmic debris. Each scenario demands different investigation approaches. Active probes might respond to communication attempts. Ancient derelicts could contain archaeological treasures from lost civilizations. Camouflage monitors might reveal themselves through pattern analysis or spectroscopic signatures invisible to current methods. The monitoring network hypothesis suggests we should expect more Oumuamua-like objects as detection capabilities improve. If such networks exist, enhanced technology will inevitably reveal additional artificial visitors, each potentially offering new insights, regardless of which scenario proves correct. Oumuamua has fundamentally altered humanity's perspective. We can no longer assume anomalous objects are automatically natural. The universe might be far more populated with intelligence than previously imagined. The immediate scientific response has been remarkably productive. Astronomers worldwide are implementing improved detection networks designed to catch the next interstellar visitor much earlier. The European Space Agency's upcoming missions will enhance our ability to spot fast-moving objects. NASA's NEO surveyor will provide unprecedented sensitivity for detecting visitors from interstellar space. These systems incorporate Oumuamua's lessons. Rapid response protocols now coordinate global observations within hours. Spectroscopic capabilities have been enhanced to better characterize compositions and detect artificial signatures. Most importantly, observation strategies now specifically search for the anomalies that made Oumuamua puzzling. Dr. Robert Wyrick captures the transformed mindset. We're no longer just looking for asteroids and comets. We're watching for anything unusual, anything that doesn't fit our models. This represents fundamental evolution in astronomical methodology, moving from cataloging the expected to actively hunting the anomalous. The implications for SETI research are equally profound. Traditional efforts focused on detecting electromagnetic communications from distant civilizations. Oumuamua suggests we might need to consider physical artifacts as equally likely evidence of alien intelligence. Consider the practicality, which is more likely to survive million-year journeys, fragile radio signals that degrade with distance, or physical probes constructed from durable materials. Advanced civilizations might prefer physical exploration over electromagnetic communication for investigating distant stars. Systems. This realization is influencing SETI strategies. Researchers are developing protocols specifically designed to identify artificial objects among thousands of natural bodies moving through our solar system. Machine learning algorithms are being trained to recognize patterns distinguishing manufactured objects from natural ones. But perhaps the most significant impact involves preparing for future encounters. If Oumuamua was indeed artificial, it won't be the last such visitor. Statistical analysis suggests we should detect similar objects every few years as detection capabilities improve. The next interstellar visitor will find humanity far better prepared. New networks will spot approaching objects months or years before closest approach, providing time for detailed study and potential intercept missions. Space agencies are discussing rapid response spacecraft designs capable of matching trajectories with fast-moving interstellar objects. More intriguingly, missions to investigate anomalous objects in detail are being seriously considered. If another Oumuamua visitor is detected early enough, humanity might send robotic probes for close-up investigation, potentially making the greatest discovery in human history. The broader philosophical implications are staggering. Oumuamua has permanently altered humanity's baseline assumptions about our cosmic environment. We can no longer take for granted that unusual astronomical objects are automatically natural phenomena. Every anomaly now demands consideration of artificial possibilities. This shift affects far more than professional astronomers. Public consciousness has been subtly but permanently changed. Opinion polls show increased acceptance that alien intelligence might be actively exploring our galaxy. Oumuamua has made alien visitation seem less like science fiction and more like legitimate scientific hypothesis. Educational. Curricula are incorporating Oumuamua as a case study in how science responds to paradigm-challenging discoveries. Students learn about questioning assumptions, considering alternative hypotheses, and maintaining rigorous skepticism while remaining open to revolutionary possibilities. If artificial objects are traveling between star systems, they represent technologies potentially far in advance of human capabilities. Studying such artifacts could provide insights into advanced materials, propulsion systems, or fundamental physics principles we haven't discovered. Research programs are being established to consider how humanity might recognize and safely investigate obviously artificial, extraterrestrial technology. These efforts involve astronomers, physicists, materials scientists, and even anthropologists, reflecting the profound implications such discoveries would have for virtually every field of knowledge. Yet perhaps the most important lesson is learning to live comfortably with mystery. Despite years of intensive study, we still don't definitively know what visited our solar system in 2017. That uncertainty isn't scientific failure. It's a reminder that the universe remains full of surprises. ʻOumuamua teaches us that some questions might not have immediate answers, and that's perfectly acceptable. Science progresses through accumulating evidence, testing hypotheses, and remaining open to unexpected discoveries. Whether our first interstellar visitor was natural or extraordinary, it has enriched our understanding of cosmic possibilities. As we scan skies for the next mysterious visitor, we carry transformed perspective. The universe might be teeming with intelligence, sending scouts between stars and vast networks of exploration we're only beginning to glimpse. Or it might be filled with natural processes so exotic that our most creative theories barely account for their existence. Either possibility fills the cosmos with wonder and promise. Oumuamua has reminded us that we live in a universe far stranger and more magnificent than we imagined, and that the greatest discoveries might be heading our way right now. Traveling silently through the darkness between the stars, the question isn't whether we'll encounter another Oumuamua, it's whether we'll be wise enough to recognize what we're seeing when it arrives.